Good morning, everyone. My name is RAJARAJESWARY and my metric number is 22, 33, and 29. Today, I would like to present a topic that is highly relevant, especially tropical countries, about post-harvest spoilage of fruits with focus on bananas. Next slide. Did you know that nearly 30% of harvested fruits are lost after harvest due to natural processes like ethylene-triggered enzymes that speed up ripening, browning, and decay? In hot and humid climates, traditional preservation methods often fail. That's why we looked into modern eco-friendly technologies like cold plasma and 1-MCP, which help delay spoilage without using harmful chemicals. This issue also ties into Sustainable Development Goal 30, aiming to reduce food waste and support farmers with affordable and sustainable innovations. Next, I would like to pass to the next presenter.
Okay, so before I start with my part, let me introduce myself. My name is NAVIN and my matrix number is 223673. So now I will explain about the case study scenario. So the main problem in this case study scenario is the banana post-harvest crisis in the southeast area. So there are several key issues that happen in this part. First one is approximately 30% of banana lost post-harvest due to their ripening and also their spoilage. This will be main caused by ethylene-induced enzymatic activity, for example, polygalacturonase and polyphenol oxidase, that will be result in fruit softening and also browning. There are several factors that contribute this crisis. First one is high heat and humidity, which is accelerate the spoilage. Second is lack of cold chain, especially in the infrastructure. Third is microbial contamination, for example, bacteria and fungi, which is handling the poor handling. Fourth is climate change, that may increase the ethylene biosynthesis that worsen the spoilage. So as an impact, from the article, 40 to 44% global fruit or vegetables become wasted. For example, the wasted resources are water, land, labor, and also energy. This will become a threat for farmer income and also national food security. Next, we look into the controlling enzymatic ripening and also the microbial spoilage. There are three examples. First is 1-SCP, which is stand for 1-methylcyclopropane, which is bind to the ethylene receptor and also delay the ripening and also extend the shelf life. Second is non-thermal technologies. We use the cool plasma, Hall electric field, and HHP, which will be further explained by my further teammates. Third one is sustainable packaging and also coatings. We use the active packaging that is contain the ethylene and also antimicrobial. And we use the edible coating as well. For example, cytosine, pectin, and alginate, which is become a barrier to gas, moisture, and also the microbes that help us to delay the ripening process and also the browning. So we can use the spray or dip as a coating. Next, I will pass to the next presenter.
Okay, let me introduce myself. My name is LETCHUMY CHONG. My matrix number is 224145. So I will be explaining about the biochemical analysis on this topic. So as all of us know, the ripening and spoilage of fruits is actually mainly cause of ethylene, which is a plant hormone. It is produced through ethylene biosynthesis pathway, which we will be discussing right now. So as in the slide, we can see that it starts from the amino acid methionine, which is converted into S-adenosylmethionine, SAM, and also converted to 1-aminocyclopropane 1-carboxylic acid, ACC. And lastly, ethylene gas will be produced. So the key enzyme that is used in this process is actually SEC synthase and also SEC oxidase. So once ethylene gas is released, ethylene binds to its receptor in the food, triggering the expression of ripening-related genes. These changes are not random, but is regulated by the ethylene signaling receptors, which is ETR1, and also the transcription factors, which is EIN3. This will cause activation of ripening genes. Next, let's talk about the key enzyme in fruit ripening and their effect. As all of us can see, first the glucuronase enzyme PG. It breaks down pectin in several that cause the fruit softening. Next, pectin methylesterases PME that will remove methyl group from pectin, which will weaken the wall for PG activity. Next, the polyphenol oxidase (PPO). It will oxidize phenolic components into brown pigments that will cause browning in fruit when it's cut. And also lipoxygenase (LOX). It will break unsaturated fatty acid into volatiles, which will cause off errors and also membrane damage. Lastly, cellulose and B-galactosidase that will degrade the cellulose and galactose polysaccharides for further softening of fruits. Next, let's talk about the oxidative stress and also the reactive oxygen species ROS. As fruit cells metabolize after harvest, they generate reactive oxygen species such as hydrogen peroxide and also superoxide radicals. While small amount of RS are involved in normal plants, it will maintain the balance between the production and also scavenging of ROS. But on the other hand, if it's overproduction of ROS or reduced activity of antioxidant enzyme, it can cause damage, which is cellular damage and also molecular damage. Molecular damage in the wise of nucleic acid damage, protein, lipid, and also amino acid. On the other hand, cellular damage includes the damage of cell or organelle, membrane, electrolyte leakage, impaired function of organelle, and also reduced metabolic infancy that will lead to apoptosis, which is the retarded plant growth and development. Next, I will go into microbial spoilage of fruits and also the temperature and humidity effect on fruit. So let's start with the microbial spoilage of fruits. The main microorganisms that include in this spoilage is fungi and bacteria, which act as the post-harvest invaders. What they do is actually they mainly secrete enzyme like pectin lysis, which will break down the pectin, cellulase that will degrade the cellulose, and also the protease to break down the proteins. And lastly, the microbial component and the plant enzyme will work together to accelerate the decay process, which will lead to softening, browning, and also loss of edibility of the fruit. Next, the temperature and humidity effect, where higher temperature can increase the enzyme reaction rate that will speed up the ripening and the spoilage of fruit. High humidity refers to the amount of moisture in the air, which will enhance microbial growth because they are mainly aerobic microorganisms, which will provide ideal moist condition for the enzymatic action. And lastly, problem in warm climates because there's no cold storage to slow down the spoilage of fruit. Next, I will pass to the next presenter.
Hi, my name is SITI SOFFEA BINTI KAMARULZAMAN and my matric number is 224594, and I want to share to you guys about how can we keep the fruits and vegetables fresh for a longer time and after they are been harvested. So we might think spoilage is just a natural and avoidable, but actually there are a lot of smart and scientific ways to slow it down. And this here is a list of methods that I will share to you guys. Next. So fruits and vegetables can continue to undergo a metabolic process even after they are harvested, and this include respiration, enzymatic browning, and cell wall degradation. And when left uncontrolled, this process will combine with microbial contamination and lead to spoilage, reduced nutritional quality, color changes, and loss of texture. In response, researchers and the food industry have been developed a variety of physical, chemical, and biological methods to manage this enzymatic reaction and aiming to preserve quality during storage, transportation, and distribution. Next. So here is solution that involve non-thermal physical treatments that technologies such as pulse electric fields, PEF, and HSP hydrostatic pressure that are effective at inactivate the enzymes and reducing microbes without relying on high temperature, which can damage the nutrients in the produce. So, for instance, PEF has been shown to limit browning and acrylamide formation in minimally processed products like potato chips by reducing their sugar and enzyme activity. And this not only improves the color and texture but also lowers the oil content during frying. Meanwhile, the HHP has been used successfully for fruits like carrots, pumpkins, and papaya to maintain their firmness and slow the enzymatic degradation. No, next slide, please. Okay. So another cool thing is we have a cool plasma that including plasma activator, the PAW. So this method use reactive oxygen and nitrogen species to target microbial cells and enzymatic reaction. Unlike the chemical treatments, cold plasma leaves no residue cells and enzymatic reaction. I'm sorry. This method uses reactive oxygen and nitrogen species to target the microbial cells and enzymatic reaction. Unlike the chemical treatments, cold plasma leaves no residue and has minimal impact on taste and texture. So, research has shown that this technique can significantly extend the shelf life of fruits and PAW also improves water's oxidation reduction potential and pH, making it more effective as an antimicrobial wash without adding harmful chemicals. And you can see it in this slide. This picture is basically PAW. So next, this is chemical dipping and vacuum impregnation. Both of these are basically additional approach that can slow enzymatic activity and also the looks like traditional methods which we dipping fruits in solution that contain calcium, salt, citric acid or natural plant extract that helps strengthen cell walls and reduce the enzymatic browning. So vacuum impregnation takes this as a step further by enabling the protective compounds to penetrate deeper into the fruit tissue. And next, so this is edible active coating, which is made from natural polymers like chitosan, arginine, and pectin. And these coating are often enrich antioxidant, antimicrobial agents, and form a protective layer on the surface of the produce. So next, this is one methyl cyclopropene, 1-MCP, that is synthetic compound that bind to ethylene receptor in fruits to prevent the ethylene, a plant hormone responsible for ripening and aging, from triggering its normal effects. So next, so this is the last one, which is biological control that using beneficial microorganisms and species such as Bacillus, Pseudomonas, and Canidia that apply to fruit surface, where we can compete with spoilage microbes for nutrient and space, produce antimicrobial compounds. And conclusion is this controlling enzymatic spoilage is in post-harvest fruits and vegetables require a multi-phase approach and technologies like I mentioned before. I hope that's all. I will pass to the RINETHAA.
Okay, next I will be continuing with Sustainable Development Goals. But before that, let me introduce myself first. My name is RINETHAA SRITHARAN. My matrix number is 225277. So, today I'll be focusing on 4 key Sustainable Development Goals, which is SDG 12, which is Responsible Consumption and Production, SDG 2, Zero Hunger, SDG 13, Climate Action, and SDG 9, which is Industry, Innovation and Infrastructure. Next slide. Okay, so let's start with SDG 12, which focuses on responsible consumption and production. So, one third of all fruits are lost after harvest during the enzymatic spoilage, especially in the climatic fruits like bananas. So, this issue not only wastes food but also the natural resources like water and land, and reduces the farmer's income. So, basically, this address so that we can use enzymatic control techniques such as 1-MPC, whole plasma, and natural edible proteins. So this technology slow down the spoilage by targeting the biochemical processes behind the ripening. As a result, we can reduce the food wastage significantly and make our production chain more sustainable. Next. Okay, moving on to SDG 2, which is zero hunger. When fruit spoils before reaching the market, the available food supply shrinks, impacting the food security, especially in vulnerable communities. So the farmers, particularly smallholders, also face unstable incomes. So natural preservation methods like chitosan-based edible coatings and also non-thermal techniques can help to keep the fruits fresh for longer without any harmful chemicals. This means no food reach consumers and improving the food access, helping the farmers can earn steady income, which will directly support the goal of the reducing hunger. Next slide. Okay, now let's look at SDG 13, which is the climate action. So when spoiled fruits ended up in landfills, they emit methane, which is a powerful greenhouse gas that will worsen the climate change. So the enzymatic spoilage is a big contributor to this problem. By controlling the enzymatic activity and extending the fruit shelf life, we can reduce the climate amount of fruit that will end up rotting. So this helps to cut down the emission from the waste and support our effort to fight the climate change through more climate-smart agriculture practices. Next slide. SDG 9 highlights the importance of innovation and in building resilient infrastructure and promoting the sustainable industries. So many small-scale farmers don't have the access to advanced post-harvest preservation method, but scalable technologies like vacuum impregnation and high hydrostatic pressure have shown promising results in improving the fruit shelf life. So this innovation will help to modernize the agriculture, making it more efficient and sustainable for everyone, from smallholders to commercial producers. So to conclude, the controlling enzymatic spoilage in post-harvest fruit handling links directly to the multiple SDGs. So it addresses food wastage, hunger, emission, and access to the technology. So by applying biochemical knowledge in this real-life farming system, especially in tropical and resource limited setting, we can create a stronger and more sustainable food system. Next, I'll pass to the next presenter.
So now I would like to give a conclusion for our presentation. The issue of fruit spoilage is not just a minor inconvenience problem, it's a serious biochemical challenge and a global sustainable control. So these solutions not only help to maintain food quality and safety, but also support our local farmers and strengthen supply chains and align with sustainable development goals focused on responsible production and food security. However, the true potential of these innovations can only be realized through greater awareness and affordability and training for farmers and distributors at every level. By investing in these sustainable approaches, we can build a future where more food reaches more people and post-harvest losses no longer hold back progress. And that's all from us. Thank you for listening.